All right, so first is linear molecules. The bond angle is 180 degrees. This is the model. And then this is the Lewis and plot diagram of beryllium difluoride. And then this is the picture of the actual molecule. And then for this molecule, there are two bonding pairs with no ionic pairs. And then polarity of this molecule is nonpolar. So the next molecule is the bent molecule. This bond angle has less than 120 degrees because there's an ionic pair. This is a gummy diagram. You can see there's two atoms and then there's a lone pair. The Lewis plot diagram is of nitrite is here. And then this is the diagram of the actual molecule. There'll be a lone pair here. And then for this molecule, there are two bonding pairs with one ionic pair, and the polarity of this molecule is polar. So the next molecule is trigonoplanar. This bond angle has 120 degrees. This is the gummy diagram, the actual diagram. This is the Lewis dot diagram of selenium trioxide. And then this is the actual picture of the diagram, the molecule. And then there are three bonding pairs with no ionic pairs for this molecule. And then the polarity of this molecule is nonpolar. All right, so the next molecule is trigonopyramidal. This bond angle is less than 109.5 degrees because there's a lone pair. This is the diagram. As you can see, there's a lone pair right here with three bonds. And then this is the diagram, but there should be a lone pair here. And then for this bond, there are three bonding pairs with one ionic pair, and the polarity of this molecule is polar. All right, so the next molecule is tetrahedral. This bond angle is 109.5 degrees. This is the diagram. As you can see, four bonds. And then the Lewis and dot diagram is here of silicone tetrahydrate. And then this is the printed out diagram. And then there are four bonding pairs with no ionic pairs, and then the polarity of this molecule is nonpolar. Alright, so VSEPR, the acronym VSEPR stands for the valence shell electron pair repulsion model. The model states that electron pairs will repel each other such that the shape of the molecule will adjust so that the valence electron pairs stay as far apart from each other as possible. Molecules can be systematically classified according to the number of bonding pairs of electrons as well as the number of non-bonding or lone pairs around the central atom. Oh, hey, I didn't see you. What is the difference between polar and nonpolar, you ask? Oh, polar, a bond between two nonmetal atoms that have the same electronegativity and therefore have equal sharing of the bonding electron pairs. And then nonpolar, a bond between two nonmetal atoms that have different electronegativities and therefore have unequal sharing of the bonding electron pairs. So the last two molecules are called tetrahedral bipyramidal and octahedral. Tetrahedral bipyramidal, this is the diagram of it. And then the subsets are sawhorse, T-shaped, and linear. And then for octahedral, this is the diagram for it. And then the subsets are square pyramidal, square planar, T-shaped, and linear. Alright, thank you for watching. If you liked it, if you want to subscribe to this video, the citations for this video are in the file below. Thank you. Oh, so you thought we were done. We forgot to discuss the dipole arrows. Alright, so for beryllium difluoride, there are two dipole arrows pointing outwards towards the fluorine because they're more electronegative. And then for nitrite, there are two dipole arrows pointing towards the oxygen because the oxygen are more electronegative. And then for selenium trioxide, there are three dipole arrows pointing towards the oxygen because the oxygen are more electronegative. And then for silicon tetrahydrate, there are four dipole arrows pointing towards the hydrogen because hydrogen is more electronegative. And then for phosphorus trihydrate, there are no dipole arrows, so we just didn't include it in the video.